All right, hello children. In this video, we'll be using the ideas outlined in our previous video on complex circuits to figure out some information about the circuits shown in these problems. These first couple are actually not complex circuits, but they're a bit of a warm-up for us before we tackle those. So we've got our power and Ohm's law relationship, and we're trying to find the equivalent resistance of each circuit. So pretending it's a circuit with just one resistor, find the total current outputted by the battery based on that. And then we got to look at each resistor individually to find their power dissipated. All right. So first, I see here, I'm doing this just algebraically, no numbers. And I have a series circuit. These resistors are in series because if I were to look at the current, there is just one current coming from the battery going through these guys. So I know when resistors are in series, I can say they have an equivalent resistance of them added together. So in this case, they're both R, so just R plus R, 2R. Great, so that means I can treat this circuit as one resistor with resistance 2R, which will make my current. Ohm's law, delta V equals IR. I is delta V, except in this case the R is not just R, it's 2R. 2R. Okay, now the power dissipated by each resistor. Now I got to go back and look at them individually. What do I know about this resistor? Well, I know it has a resistance R, and I know it has a current going through it of delta V over 2R. So I can say, I made a table. I have resistor 1 and resistor 2. They both have resistance R. Then they both have delta V over 2R. Or delta V in this case, sorry, is just the voltage of the battery. Actually, no. Yeah. Because if I look at this, I gain V, I lose V. So total current, the battery, V over 2R. Now, the delta V for each resistor is not V, because together, if I go around this loop, they take away V. Here it was V because I made them one resistor, but now they each do it. Shortcut here, these are the same resistance, so they each are going to do half. But if I wanted to see that, I could use Ohm's law, delta V equals IR. I is V over 2R, R is R for one resistor. So I multiply these together, I get delta V is V over 2 for both. And the power, I could do I squared R, or I could do I times V. And we get V squared over 4R. Same deal here, V over 2 times V over 2R is V squared over 4R. If I were to do the battery in my table, it has a current V over 2R. V, I would find it has V squared over 2R as its power, which is good because when I add these two resistors up, I get the power from the battery. B. So this is similar, except now I actually have numbers. I'm going to call this resistor 1 and this one resistor 2, just to keep things straight. I'll make a table. It's probably not necessary for a circuit like this. That's not super complex, but you can do it anyway. All right, first thing we want to make an equivalent resistor because that's what it's asking us for. I can see these and trace the current. These are in series. They have the same current going through them. So I can add them together. For my equivalent resistance, REQ equals 5 ohms plus 10 ohms, so 15 ohms V. All right, so my current through here is 9/15 amps, which I can simplify, divide both by 3/5 amps. This would be 0.6. So R1, 5 ohms, R2, 10 ohms. Don't have room here to write the units. Battery resistance isn't a thing for batteries, in this class at least. 3/5 amps. Same current through all of them. All right, delta V for the battery, it's 9 volts. It's not going to be 9 for these guys though, because they are, if I colored this, dropping the voltage by a different amount each time here. But I have Ohm's law to tell me how much. Delta V equals IR. 5 times 3/5 is 3 volts, sorry. That's why we should include units. 3/5 times 10 is 6 volts. And this is nice because I see, okay, it gains 9, loses 3, then it loses 6. It goes back to 0, so that works out. That satisfies conservation of energy. Double check that by looking at power as I times V, or you could do I squared R. So 9/5 watts, 18/5 watts, and 9 times 3 is 27/5 watts. You could have written these as not fractions, whatever. This plus this is this. Great. Energy conserved. Charge conserved easily because it's one loop. All right, here we have a parallel situation. Again, we want to get one resistor. In a parallel case, we use this relationship. And that gives us 2/R. But 2/R equals 1/REQ. So REQ, I have to invert. It's R/2. Let's think about this conceptually. If I, for a second, just ignored this part of the circuit, I'd have a current I going around. When I add another loop here, it's the same resistance. So now I have 2 loops that would have that current, which means this is getting that current, this is getting the current. So the battery then is making twice as much current, which is just like as if I had 1 loop, but half the resistance, because that would also give me twice as much current from the battery. This is I. It splits into I/2. Oops, sorry. Should really. I1, I2. We call this 1 and this 2. And I found here that the total I didn't find it yet actually. For this delta V equals IR. So here, this R equivalent is R/2. So I is equal to delta V, which is just V of the battery divided by R/2, which is 2V over R. I didn't really get myself enough room for my table on this one. All right. So that's the total current. Now, when I go back and look at finding the power for each resistor here, I have to remember that because this is a parallel circuit, that power, that current they're getting is not this full current. They only get a portion as it splits into I1 and I2. 1, 2, R. So while this table looks initially just like our table for the last one without numbers, the currents and things are going to end up being different than that previous table because we are in parallel. All right, so here it might help. Throw some colors on here. Circuits love colors. And I can see batteries adding a certain amount. Each of these resistors taking away that same amount. So while I don't know the current through each of these resistors just yet, I do know using Ohm's law, I can find it because this is going to be V and this is going to be V. This is going to be V over R and V over R. And you'll notice that's half as much as what we found the total current to be in our equivalent resistor, the current from the battery. So the battery's putting out 2V over R and it's splitting in half. Half is going one way, half is going the other. So power here, V squared over R, V squared over R, 2V squared over R. Energy conserved once more in the power line there. All right, numbers usually helps. All right, so same deal, I have a current I, and it's also going all the way here, and splitting into I1 and I2. I call this 1, and this path 2. All right, we could do the equivalent circuit. Where I have 1 over REQ equals 1 over 2 plus 1 over 4. 1/2, I can double that to 2/4, so that's 3/4. Therefore, I have to remember to flip it back. 4/3 equals REQ. Again, this is the most common mistake I see with doing this process is not flipping it, because this is 1 over. I have to switch it to get just this ohms. Okay. Well, if I know the ohms, the resistance of this guy, 4/3 ohms, then the current I delta V equals IR. My V is 80. So I equals 80 volts over 4/3 ohms. It ends up being 60 amps. Great, so I can go back and say this is 60 amps. From the battery. 1, 2, R, I, delta V, P. Two, 4. All right, I in the battery, 60 amps. Delta V from the battery, 80 volts. And as we saw in the last question, if we look at are equal potential areas that, according to our thing here, blue to red, both these have to be dropping 80 volts. So that if I go around either path, I get back to where I started. So we can use that to find our current here. Delta V equals IR, so I is delta V over R. 40 amps. This is an insane amount of current, by the way. Each of these wires would melt, probably. 20 amps. But since they're ideal wires, they will not melt in our perfect world. Great, and current is conserved, charge is conserved. This 60 splits into 40 and splits into 20. Great, power. Insane amount of power here, 8 times 4. I can do that, 3,200 watts. 1,600 watts. 6 times 8 is 800 watts. One thing to note here, because in science we're trying to recognize patterns, they said half the resistance is this. So if I think of my total here is 6, this gets 1/3. This gets 2/3, this gets 1/3, sort of flips a little bit. Half the resistance, twice the current through it, comparatively. Because they need to end up with the same voltage drop. I think I answered everything I needed on that one, yep. All right, we get to our first complex circuit. So immediately my gut reaction is to identify the different areas of potential. All right. So the battery is adding a certain amount of potential. This resistor is taking some away. Then the electron either goes this way and loses more, or goes this way and loses more. Or the charge, I should say, really, the electrons are going this way. Right. I need to do an equivalent thing here because I don't know how much this resistor is dropping the voltage. Like if I drew a table, if I called this 1, 2, 3, Ri delta Vp. Eight ohms, 30 ohms. You can see as we go along, my ohm symbol gets worse and worse. I have the battery on here. I don't know any of these I's. The battery is supplying 100 volts. But I don't know any of these because I don't know what the orange is. If I knew what this orange area was in terms of potential, I could find the delta V's for all of these, but I don't. I don't know anything about power. Now, if I can find the current from the battery, if I look at my currents, I've got this current going through the battery and it's splitting up. Call this I2 and I3. If I can find this current, well, that'll let me know things about resistor 1. I can find the delta V there. I could find this orange area. If I know this orange area, I can now find these delta V's. So that's my rationale here. Even if I wasn't asked for the equivalent resistance, I would have to find it in order to solve anything about this circuit. So where to start? Can I do anything to combine this 8 ohm resistor? Well, there's nothing with the same current and there's nothing doing the same voltage drop. So I can't do anything with this. These guys, different currents, so not in series, but same delta V. So they are in parallel. I can combine those. So my 8 ohms still here. And now I have this guy, it's a combination of 2 and 3. And that was in parallel, so 1 over R2, 3 equals 1 over R2 plus 1 over R3. All right, 1 over 30 plus 1 over 45. If I couldn't recognize the common denominator here, I could just multiply this one by 45 and this one by 30 to get 30 times 45 on the bottom for both of them. But I can see here that this twice this is 90, 3 times this is 90. So this is, I can multiply this side by 3 and 3. I can multiply this one by 2 and 2, which gives me 3 plus 2 is 5 over 90, which is 1 over 18, because 5 times 20 would be 100. So, and then I need to flip it to get REQ. Or I guess this case I'm calling REQ R23 is 18 ohms. Great. And now, well, these are all in series. So I could again R123, and series is easy. I just add them, 26 ohms. The volts was 100 volt battery. So now I can find the current here. It's going to be 100 volts over 26 ohms. That's not a pretty number. It's 50/13. I'll leave it like that, though, in case the math gets nicer later on. But I guess Mr. Vogt, when he made this, maybe didn't make the numbers work out. If this had come out to 25, we'd be in a little bit better shape here. All right, so 50/13 is the current from the battery. If you're doing this, if you just want to find what number that is, go for it. But I'm going to see if it actually ends up working out mathematically any better. In case I want to change the numbers for next year. Are any of these actual, or is this just getting that 50/13? Well, yes, the 8 ohms one is. Great. These guys are not, because it splits. Well, now I can find this. I look at my table, I know two things. I can find a third. 8 times 50/13. Yeah, there's no way that this is a number that comes out nicely. So maybe we should just find out what that is. 8 times 50 divided by 13. 30 point, I'm going to round, 30.8. The thing about rounding is now we're not going to get a perfect addition of power, but that's okay. All right, 30.8 volts. Can I use that somehow to help me figure out anything else? Well, I say this is 100. Because if I call this side 0, then I gain 100. Well, 100 minus 30.8 is 69.2 volts. And now, you know, I just found something here. So I just did this just to see what happens. Now I see, does that help me find anything I'm missing in my table? And it does. Because now I know I'm going from 69.2 to 0 over each of these resistors. Because if I think about a path an electron could take, you know, it could go over 1, over 2, and back. So it goes over the battery, it goes over 1, it goes over 2. Well, those add up to 0 because these take away. Or it could go over 1, over 3, and back. So over the battery, over 1, and over 3. Both of those cases conserve energy. Nice. So we're not looking to add these things all up, but we should, if we take a specific path, battery 1, 2, or battery 1, 3, we should get back to 0. All right, now I can find what these currents are. 69.2 divided by 30, 2.3 amps, 69.2 divided by 45, 1.54 amps. What is 50 divided by 13? 3.85. So this is actually 3.85 amps, which if I add up 2.3, 1.5 is 3.8. Yeah, works out. Again, we might have some straggling decimals because we're rounding. All right, so this is power of 385 watts, 1.54 times 69.2, 106.6 watts, 2.3 times 69.2. Oh, there's something wrong there. 2.3. 159.2 watts. And 3.85 times 30.8. 118.6 watts. Let's see. 120, 280, 386. Yeah, close enough given the rounding. I accidentally start a recording here. How do I delete that? No, don't worry about it. All right. F. Let's see. I gotta pause for a second. All right, we're back. Put some colors. I'll just do the orange layer because I like doing red and blue. We gotta have a bunch of colors for this one. All right. 4 different potentials. 0, 50. And I don't know the purple or the orange here because I don't know any currents yet. Speaking of currents, here's one loop. Here's another one. Here's another one. So we could call this I because it's the one that the battery has. I'll call this one resistor 1. Just follow the currents around. 2, 3, 4. So this could be I1, and this could be we could call it I2 or I3 or just I23. It's the current that's going through. Let's just call it I2. Just keep it simple. But we'll remember that the current through I2 is the same as the current through I3. So I is splitting up into I1 and I2. And coming back together. So this resistor 4, is getting the full I there. Let's draw a table. R, I, delta V, P. Oops. 4 resistors in the battery. 1, 2, 3, 4 in battery. Great. Batteries don't need that part. 50-volt battery. Then we have 40, 100, 20, 20. And do I know anything else? Nope. I don't know any of these voltage drops because I don't know purple or orange here. All right. So I need to do something. Well, if I have all the resistors, so I can find the equivalent resistance. I can find I. And that can maybe help me, because if I can find I, well, then I know about this resistor, because it has I. So I can find this orange. Well, if I know this orange, I know the blue, I can find this resistor. And if I know this current, and I know this current, I can find that current, and I can find this stuff. All right. So this one's going to take a couple steps to simplify. I can put the 20 and the 100 together. That's 120. Was that 20? 20, 40, 120. I've gotten rid of this purple, so now these have the same change in voltage. If I were to, oops, color that. I would see that. So this is now like this. Notice when we combine the parallel resistors, they keep the same delta V over their equivalent version. And all that. Oh, I need to figure out what that is. This one's 20. This one we have 1 over 120 plus 1 over 40. So I can multiply by 3 is 4 over 120. Now I gotta flip it to get 120 over 4 is 30 ohms. All right. This one the math worked out, okay. $50 ohms. It was a 50-volt battery, yeah. All right, that other question, gotta fix it. Make the math easier on future generations of students. So I have a current I, 50 over 50 is 1 amp. Great, so I go back to my original. I say this is 1 amp. All right, how does that help? Well, 1 amp here, it's also 1 amp through 4, because when I drew my currents, I could see this is all the same. Well, that means this is changing the voltage here by V equals IR 20 volts. How does that help? So this is 0. This has to have been 20, because it took away the 20 to get back to 0. Okay, well, and you'll notice this is the process we outlined earlier, what we were going to do. We're doing it. 20 to 50, that's a change of 30. So resistor 1 is a delta V of 30 volts. Well, now I can find its resistance. I mean, its current. Delta V equals IR, so 30 over 40 is 0.75 amps. Well, how does that help me? I go back here, I label resistor 1, 0.75 amps, going through it. Aha, 1 amp. 3/4 of it goes this way. The other quarter has to go that way. So I2 has to be 0.25 amps. Add that to my table. And it's in series with resistor 3, so they both have that 0.25 going through. Great. 100 times 0.25 is 25. Because why not fill out the rest of this table, right? 20 times 0.25 is 5. This is good because we know this has to be a change of 30. So if I change it by 25 and then change it by 5, I've changed it 30. So for those curious, this would be 25. The purple, we would call 25 volts if we wanted to, but we don't need to. Power, I'm just multiplying 75 times 0.3. 2.25 watts. 0.25 times 25. 6.25 watts. 0.25 times 5. 1.25 watts. 20 watts. 50 watts. That doesn't add up, does it? Let's pause this and figure that out. 30 times 0.75 is 22.5. So now let's check. 22.5, 28.75, 29, 30. 30 plus 20 is 50. Nice. The remaining resistor. It's a 400 volt battery. Blue. Great. Define this as 0. Makes this 400. Don't know the orange. All right, so it looks like I'm gonna have to do some equivalent resistance stuff here. Let's make our table first though, to make sure. We'll say 1, 2, 3, 4. And we can draw currents. We got the main current from the battery, I. Splits, I1 goes this way. And this goes down here and it splits up into I2 and I3. Those come back together. To make I4. And I4 and I1 come back together to make the original I. All right. Yeah, so we're definitely gonna probably need to do some equivalency. 1, 2, 3, 4, and battery. $40, 20, 80, 24. 24, wow. 40, 80. Oops, wrong order. 1 is 40, 2 is 20, 3 is 80, 4 is 24. Delta V for the battery is 400. Yeah, that's everything I'm given. So looking at my table, I see I don't have anywhere where I know two things, but I know all the resistors. So I can find equivalent resistance and find the battery current. All right. So what are we going to combine here? Nothing shares a current and a drop here. All right. These are in parallel. Let's put those together. And when you get good enough at this, you don't have to draw the new circuit out every step, but for now, you should practice that. So this is going to be 1/20 plus 1/80 equals, I can multiply 4 and 4 here, 5/80. Flip it, 80 divided by 5 is 14, or 1, 2 equals 14 ohms. Yeah. No. 5 times, no, that's not right, 16. 5 times 6 is 30, 5 times 10 is 50, yeah. Okay, so we've got 16. We've got 24 and 40. I'm not going to color code this and everything again because I can see right away. I can put these together. Battery, 40. Oh, 40 and 40. Battery is 400. All right, these are in parallel. Now you can do the math, 1/40 plus 1/40. Or I can say, well, 2 resistors in parallel is like 1 resistor with half the resistance. 20. Because 2 paths means it's like there's twice as much current, which means it's like there's half the resistance. 400 volts. Well, now I can find I. (40/20). Cancel 0, 40/2, 20 amps. An insane amount of current, but living in an imaginary world anyway. So let's add that back to our original here. 20 amps. That's through the battery. And that's it. It's the only one that gets 20 amps. Oh, there was something I could have done originally. I do know that delta V over the 1 ohm resistor is 400. Because this resistor is in parallel with everything else here. And we saw that when we combined them. Whoops. So we can add that 400 to resistor 1. Which means the current, 400 divided by 40, 40 divided by 4 is 10 amps. So let's add that here. All right. So 10 amps going that way. That means 20. We had 20 total. So 10 are going this way. It's splitting up into I don't know what, but then it's coming back together to be 10 again. So I4 has to be 10. Another way I could say it is, well, there's 10 going in, 20 coming out, 20 has to be going in here. So the fourth resistor, 10 amps. Hey, 24 and 10, oops, that's 240 volts. Back to my picture, 240, starting with 0. This is 240 volts by reference. 240 on one side, 400, that's a change of 160 for both of these. Now that we have all those voltages, let's just double check by taking some electron paths, or pretend positive charge paths going this way. All right, gains 400 over the battery, loses 400 over resistor 1, perfect. Gains 400, loses 160, loses 240, great. Gains 400, loses 160, loses 240, perfect. We can fill in the missing info here. 160 divided by 20 is 8 amps, 2 amps. This is good. 8 plus 2 is 10, which it needs to be, because 10 is turning into 8 and 2, and back in 10. Power. 4,000 watts. Wow. This is a stupid amount of power. 8,000 watts. 240,000 watts. 8 times 16. 8 times 6, 48. See, we did all the math right. 4,000, 5,000, 280, 5,600, 6, 5, 7, 8,000. Yep. All works out. Should we leave this bonus for another video?